Okay, so welcome to lecture number 2 of electrical machines. So we'll continue with that, but before we go ahead, few of students, I think yesterday, what problem we are doing on maximum transfer theorem, that was actually wrongly calculated. Somebody pointed out it after the class. I forgot his name, but he has exactly pointed out that the Thevenin voltage is not 45 voltage, what you have calculated. It is in fact 70 volt. Okay. So how it is, you can calculate from here, right? By applying KVL, you can find the voltage across this, right? So how will apply KVL here? You can see here minus 100 volt plus 20I plus 30I plus 25 is equal to 0. Now your I equal to 75 by 50. So with this current, we have to find the voltage across AB. So the voltage across AB will be, that is nothing but V Thevenin. So that is equal to 100 minus 20 into 75 by 50. Okay, so it will give me around 15, 30. So it is 70 volt. Okay, so it will be 70 volt. Okay, please. If somebody has done wrongly, please make it correction. Okay. So it will be 70. Then your net current through the RL will be 70 by 24, 12 plus 12. And maximum power transfer will be I square R. So 70 by 24 square into RL, whatever RL is 12 ohm. Okay. So this is your maximum power. Okay, I hope yesterday we did little bit wrong, so I hope everybody understood now. Okay, and also we are discussing the instantaneous power where we talked little bit how this waveform came. This power waveform, you can see this is your voltage waveform and this is your current waveform, and the phase difference between voltage and current is theta. And how this power, instantaneous power waveform came. In fact, we are deriving that I can write it here as Pt equal to Vt right? So again, I can write it equal to Vm cos of omega t plus alpha into Im cos of omega t plus phi, right? And that I can write, up to this we have done already, Vm Im by 2 cos of alpha minus phi plus cos of a minus b plus a plus b. It is cos of 2 omega t plus alpha plus phi. Already we have done this up to this. And little adjustment we Bm by 2, Bm by root 2, Im by root 2, I can write Vi, right? Vrms, Irms into cos of alpha minus phi is nothing but equal to theta. So I can write it here theta cos theta plus, just expanding this, I'll find cos of 2 omega t to cos of alpha plus phi minus sine of 2 omega t sine of alpha plus phi. Again, I can little bit readjustment I can do here, just manipulation. Here I can write cos of alpha minus phi into cos of alpha plus phi by cos of alpha minus phi into cos of 2 omega t minus cos of, sorry, minus sine of alpha minus phi into sine of alpha plus phi by sine of alpha minus phi into sine 2 omega t. Okay. So this will give me bi alpha minus phi is theta, so I can take cos theta common. So vi cos theta 1 plus whatever, it is a constant, right? I can write it k1 cos of 2 omega t, then minus vi sine theta, sine alpha minus phi I can write sine theta, and this is also a constant, so I can write k2 sine of 2 omega t. Okay. So this is what it represents. This power, in fact, this power is plotted based on this equation, right? Power plot PT, right? And this in fact gives us, sorry, this gives us the real power, right? And this gives us reactive power. This is your real power or active power, and this is your reactive power. Okay, so if we'll take the average value of this real power, it will be Vi cos theta, right? Okay, but whereas if we'll take the average value of the reactive power, it is 0. So therefore reactive power is not active. It doesn't do any work in fact. So therefore the average value of the reactive power is 0. And in fact, the average value of the real power is Vi cos theta, right? Therefore, we represent P, that is the real power, as Vi cos theta. This is in fact the average value, right? And Q we represent Vi cos sine theta, right? Though this is not the average value, this is we can say the part of the uh, reactive power, right? So therefore represent Vi sine theta. Okay, so this is the explanation how this PT is being derived. Okay, so now next we'll move to uh, the problem what we are talking about in the last class. So this is your problem. So we have a circuit where we have 3 elements given. So the resistive element is 3 ohm and the inductance is 1 millihenry and the capacitance is 200 microfarad. And the voltage source is given here Vt equal to 14.142 cos of 1000 t. So now the question is here, find the current in the circuit. That means current in the time domain we need to find, and draw the power diagram and the phasor diagram and sketch the input voltage and the current in time domain. Okay, so if what we'll do then, we'll analyze the circuit under steady state. That means we'll find the phasor quantities, then we'll again convert it back to the time domain. Okay. Now if I'll convert this voltage into the phasor quantity, so it will be how much? It will be V equal to 14.142 by root 2, and the angle is 0. Phase angle will be 0. Okay, so this will be nothing but 10 angle 0. Okay, now considering this voltage source, now I can find, and omega is 1000, we know here, right? 1000. So now substituting omega, I can find the reactances across this inductance and the capacitance. So here it is j omega L, here it is minus j of omega C. Then I can find the net impedance and I can find the current. So the current equation will be Vy z, so nothing but v by r plus j omega l minus 1 by omega c. Okay. So this will be your equation, and utilizing this equation we can find the current expression, right? So you can see here the diagram in the phasor form. So V is tan 0 degree phase angle, and now the current we need to find. So the current equation is V by Z. So net impedance is 5 angle minus 53.13. So from this equation I can find current is equal to 2 ampere magnitude and 53.13 is angle. Okay. Now the question is, draw the phasor diagram of current and voltage. So voltage is having phase angle 0 degree. So it will lie along the real axis, and current is having phase angle 53.13 degree. So therefore it will lead the voltage by 53.13 degree. Okay. Now if we'll plot the power triangle, so before that we should calculate the power being supplied by this source. So how will calculate the power? So real power is Vi cos theta. So what is theta? Theta is 53.13 degree. Now just substituting the values, V is equal to 10 and current magnitude is 2 cos of 53.13. Okay. So this will give me the real power, that is nothing but it is coming 12 watt. Okay. Now your Q is Vi sin theta. So similarly I can put 10 into 2 into sine of 53.13. Okay. So this will give me minus 16. Why it is coming minus? Because here your, if we'll calculate apparent power Vi star, then this is nothing but Vi conjugate. So I conjugate will be your, let us substitute the values. V is tan 0 and I is your 253.13 conjugate. So it is coming 10 into 2 minus 53.13. 13, right? So this is nothing but 20 cos of 53.13 minus 20 sine of 53.13. So this is your real power and this is your reactive power. So therefore it is represented in the negative form, right? So Q is minus 16 and which is lying in the negative part of the imaginary axis. Okay, please mute yourself. Okay. Now you can find the apparent power. So apparent power is nothing but the square of P square plus Q square root, so it will come 20. Okay. So this is your power triangle. Now next question is sketch the input voltage and current in the time domain. So in order to plot the voltage and current in the time domain, we need to convert the voltage and current in the time domain. So your voltage in the time domain is given already, right? So it is 14.142 cos of 1000 t, right? And we need to write the current equation in time domain. So the current phasor is given, that is 253.13. So I can write it as root 2 into 2. 2 is RMS value here. So in order to find the maximum value, I can multiply root 2. So root 2 into 2 cos of omega t, phase angle is 53.13, right? Okay, so now your current equation in time domain will be 2 root 2 cos of omega t plus 53.13. So now if we'll plot it, your current, it looks like this. Okay. So it will lead the voltage by 53.13 degree. Okay. So now we got the solution of this problem. So we'll move forward. So now we'll do the analysis of three-phase circuit. Unlike a single-phase circuit, this three-phase circuit analysis is little complex, because when we consider three-phase circuit or three-phase sources or three-phase load, so if we consider a three-phase source, the phase angle between each phase is considered to be 120 degree. That means each of the phase is 120 degree out of phase of the other phases. Okay. Now we can see here, this is one of the figure where we are representing the voltage sources, three-phase voltage sources. It is in the star connected fashion, right? So here we are connecting a three-phase load to the three-phase source. So your three-phase source is represented by VN, BVN, and BCN. And similarly, we can also represent a three-phase source in the delta fashion as well. We can see here the delta connected sources VAB, VBBC, and VCA, right? Here VAN represents the voltage across A to N. That means voltage from A to N. And VBN represents voltage from B to N. N is the neutral point. And VCN represents voltage from C to N. Okay. Similarly, in case of delta connected configuration, VAB is the phase difference between voltage difference between phase A and phase B, and VBC is the phase difference between phase B and C. BCA is phase difference between C and A. So let us now focus on the star connected configuration. Okay. So for star connected configuration, if I'll represent these voltage sources considering VAN as the reference voltage, then I can write VAN equal to root 2 V cos omega t, where V is your RMS value and this time domain quantity, if I can convert, if I can represent in the phasor form, I can write it VAN equal to V 0 degree, because the phase angle is here 0 degree. Similarly, the voltage of phase B, VBN, I can write root 2 V cos of omega t minus 120 degree. So when we consider the positive sequence configuration, always the phase B will lag by 120 degree and phase C will lead 120 degree to phase A. Okay. As is shown here, right? And in the phasor form, obviously VBN will be V minus 120 degree and VCN is V 120 degree. Okay. So this is the positive sequence representation, right? That means if I'll represent here BA, then I'll write VB here because VB is lagging. This is positive sequence representation, and this is your VC. That means your VB is lagging by 120 degree, okay, and here VC is leading by 120 degree. Okay. This is called positive sequence representation. Similarly, if I can do the same thing for negative sequence representation. In negative sequence representation, I can show that VB is leading VA. Here it will be VB, and here it will be VC. VC is lagging by 120 degree, and VB is leading by 120 degree. So this is negative sequence representation. That means your VA, VB, and VC phasors, if we'll see clockwise direction, this is the rotation in the clockwise direction, VA, VB, VC, right? So when we'll move in the clockwise direction, that will give us positive sequence representation. And when we'll move in the negative direction or anti-clockwise direction, that will give me negative sequence representation. Okay. So I hope up to this everybody is clear. Now we can see the time domain representation of three-phase quantities. That is VAN, VBN, and VCN. They are represented in time domain, right? Obviously, VBN is lagging by 120 degree. This is for positive sequence representation. Positive sequence, okay. And VCN is leading VAN by 120 degree. Okay. Now, if we'll find the line voltage for this circuit, you can see here for the star connected configuration, if I'll find the line voltage VAB, that is the voltage difference between phase A and B. So this VAB I can write here as VAN minus VBN, because VAB I can write VAN plus VNB, right? And now I can write it as VAN. So VANB I can write it negative of VBN, right? So therefore it is VAN minus VBN. If we'll apply the KVL also in that circuit, you will find it as this. If we'll apply KVL here, if we'll apply KVL here, you will find VAB equal to VAN minus VBN. Okay. Okay. So similarly, your VBC is represented VBN minus VCN, and VCA is represented by VCN minus VN. Okay. So now this the value of VAB, VBC, and VCA is represented here in the phasor form. If I say that already VAN, we have represented it as capital. In the phasor form, we have represented V0 and VBN as V minus 120 degree and VCN as V 120 degree, right? Okay. So now if I'll find the phasor difference between VAN and VBN, so it will become √3 times V 30 degree. How it becomes like that? It is obvious from the phasor diagram. If I'll plot the phasor diagram, you can see it here. This is your VAN, this is VBN, this is VCN. Okay. Now if I'll find VAB, that is nothing but VAN minus VBN. So minus VBN, I can write it here. So this is minus of VBN. And now if we'll take the resultant of this is your VAB. Okay. So this VAB is leading 30 degree by VAN. So VAB is leading 30 degree from to VAN, right? And the magnitude obviously will be, it is root 3 times V. Okay. So therefore it is mentioned here root 3 30 degree, because VAN is lying with the reference, right? This is V 0 degree. So therefore your VAB will be root 3 V 30 degree. So that I can write root 3 V is nothing but VL. I can represent it as VL. So therefore it will be VL 30 degree. Similarly for VBC, I can find, if I'll find VBC, that is VBN minus VCN. So it will be VCN somewhere. Then the resultant will be here. This is VBC. So VBC is, in fact, it is lagging by 90 degree to VAN. So therefore, I can write minus 90 degree, the phase angle, right? So that that will become root 3V minus 90 degree. And that is equal to VL minus 90 degree. Similarly, you can find VCA also. So VCA will find that it is leading by 150 degree. Okay. Okay. So now if we'll see the current here in the star connected configuration, the sum of the current IAN plus IBN plus ICN, the phasor sum of the current will be equal to 0. You can check it yourself, right? If I'll write IAN as sum, IAN as theta, IBN as I of theta minus 120, and ICN as I of theta plus 120. Just take the phasor sum of this, that is IAN plus IBN plus ICN. That will give me I theta plus I theta minus 120 plus I theta plus 120. Just to find the summation, you'll find it 0. Okay. So this will give me 0 value, right? Now if we'll find the line current, that is, what is line current? In fact, we can see it here. The current flowing in the phases, that is known as the phase current. And the current flowing in the line itself, we call it line current. So here if we'll see in the star connected fashion, your line current is equal to the phase current, right? But in case of delta, it is not. Your line current is not equal to the phase current, because your phase current is here somewhere, right? This is your phase current, and this is your line current. So here line current is not equal to the phase current, but here your line voltage is equal to root 3 times phase voltage. This is a magnitude, huh? Okay, only magnitude. So this is the relationship, and here also we'll find the relationship IL magnitude will be root 3 IPH. We can see it, right? Okay, so now we'll move to the next slide. Okay, now we'll consider the delta configuration. So the delta configuration, if we'll see, so these are the phase voltages VAB, VCA and VBC. And in fact, if you'll see the line voltages, VL, they're equal to the phase voltage, right? VL I can write equal to VAV. That is equal to the phase voltage, right? Whereas the current is different. So here the voltages, the voltage phasor is given in this manner. VAB is equal to V 0 degree, VBC equal to V minus 120 degree, VCA equal to V plus 120 degree. And if we'll apply here KVL and we'll sum all the voltages VAB plus VBC plus VCA, that will become 0 obviously, because this is nothing but V0 plus V minus 120 plus V120. If we'll expand this and add these values, it will become 0. Okay. Similarly, if we'll see the current, the phase current is not equal to the line current. So if we'll find the line current here, that is I small a capital A, then which is equal to how much will be it will be equal to VBA minus BAC, right? So VAC is flowing in this direction. So I small a capital A will be IBA minus IAC, right? So if we'll take the phasor, so the phasor will be obviously give, similarly you can draw the phasor and you can find it. It will give me root 3 times IBA minus 30 degree. So it will lag the phasor of IBA by minus 30 degree. Okay. Similarly, you can draw the phasor diagram for both positive and negative sequence currents, and you will find that for positive sequence current, your line current will lag minus 30 degree to the IBA, the phase current. Whereas in case of voltage in the star connected, we have seen for positive sequence, the line voltage is leading the phase voltage by 30 degree, right? But here it is in fact just opposite. The current is just reverse. In case of voltage, for the negative sequence representation, the line voltage will lag. So we can summarize here. For positive sequence representation, your line voltage will lead the phase voltage by 30 degree. And your line current, this is for star connected system. For delta connected system, your line current will lag your phase current by 30 degree. Okay. And similarly, for negative sequence, for star connected, your VL will lag VPH, that phase voltage, by 30 degree. You can check it yourself, right? For negative sequence, I have not explained. You can check it yourself. For delta connection, your line current will lead your phase voltage, phase current, by 30 degree. This is very important to know and remember this. And you can check all these things. Already I have shown the demonstration in this case, that is positive sequence star connected network, right? Already I have shown. You can check it for negative sequence star connected and delta connected networks, right? Okay. So now this is all about the sources, three-phase source. Now coming to the three-phase load. So similarly, as we have seen, the the three-phase source is represented through star and delta fashion. Similarly, your three-phase load also represented through star and delta connection. You can see here your loads are connected in star, either star connection or delta connection, right? We don't know here the source is connected either star or delta. And here also we don't know whether it is star or delta. Okay. But we can match it just by converting it. Suppose we have a star connected source here. We can convert. Here no need of conversion because the source is already in the star connected fashion, right? So now if we'll have a delta connected source here, so I can convert this star connected load or star connected impedances to delta connected impedances, right? And then I can do the calculation very easily, right? Okay. So similarly here, if I have a star connected source, then I can easily do it converting this load into star connected, right? Then I can do the analysis very easily. So the analysis will be easier, right? So therefore delta to Y transformation plays very important role, and the formula for transformation of Y delta to Y and Y to delta is this, which is applicable for the balanced load only, not for unbalanced load. This is for balanced load. Okay. So for balanced load, it is applicable, that is ZY star is equal to Z delta by ZY equal to Z delta by 3. Okay, this is the conversion formula. So already you have studied in your basic electrical courses, so no need to discuss much. A star delta conversion and delta star conversion. Okay. So now this is a problem. So we have to do this problem in steps, and please tell me the answer. I hope you must have the calculator with you, the scientific calculator, which in fact useful during the complex calculation. Okay. So the problem here is, so there is a balanced three-phase source, and the RMS value is given here, 866 volt. This is your line to line voltage. This is line voltage, and 60 hertz. Okay. And there is a, sorry, this is a Y connected source. Okay. And this feeds a balanced delta connected load. That means your source is like this. Okay. And your load is like this. That is delta connected load. Okay. So now this load is connected via 100-kilometer long transmission line or transmission wire. Okay, 100 km. And the impedance of each wire of the transmission line is 1 plus J2 ohm. This is also 1 plus J2, 1 plus J2. And the line to line voltage is given here. It is 866 volt. Okay. And the per phase impedance of the load is given here. That is 177 minus J246 ohm. For each phase it is equal. If the phase sequence is positive, let us assume the phase sequence is positive, then determine the line and the phase currents. So the line current will be obviously here, flowing in that line, transmission line, and the phase current is here. Okay. So find the line and phase currents, the power absorbed by the load. So power absorbed by the load and the power dissipated by the transmission line. Okay. So we need to find this, and phase current and line current. So please do it. I am giving you 5 minutes. Please tell me the answer. So the process I am telling you, just convert this delta configuration into star configuration, and as you'll convert this into star configuration, and it is a balanced network, and we can do the single phase analysis on this. So through the single phase analysis, you can find the current, line current, and then you can apply this line current in the delta configuration. Okay, so do it. I hope everybody can do this. So let me explain you a little bit. Then just very simple. So when we convert this to star configuration, this delta load, so it will become just divided by 3. So it will become 59 minus J of 82 ohm, right? Now if we'll find the phase voltage, so your phase voltage will become 866 by root 3, that is nothing but 500, and if we'll take as it as reference, it will become 0 degree for phase A, right? So then, because it is a 3-phase balanced network, I can do the analysis. So now your circuit became like this: 3-phase source, star connected to 3-phase load, star connected. And this is a balanced network, so therefore I can represent this into a single phase network and I can do the analysis. So by representing the single phase network, so for single phase I have the per phase voltage is 500 0, and the transmission line impedance is this one J2, and per phase impedance is 59 minus J82. Okay, now this is the per phase analysis I can do, and I can find the current here. So the current will be how much? If I'll calculate the Z, the net impedance, I can add these two impedances, this and this, and then I can find the net impedance. It is coming about 100 minus 53.13 degree. Okay, now I can find the current. So the current will be voltage by the net impedance, that is 500 by 60 minus J80, that is 100 minus 53.13, that will give me 553.13. Okay, this is your current, and this current we can see it is leading the voltage by 53.13 degree, therefore it is a capacitive network. Okay, now if we'll find the power factor, so the net power factor will be cos of 53.13, so that will give me 0.6 lead. Okay. So please unmute yourself. Somebody has, please mute yourself. Somebody has unmuted. Please mute. Yes. So now I can convert again I'll come to the original circuit. So in the original circuit, if you'll see, the balanced sources will be 500 0 degree, that is VN, and VVN will be 500 minus 120, and VCN will be 500 plus 120, and it is connected to that delta connected load, and the current in the line is 553.13, right? And here if we'll find, so the current in the line also it will lag by one in current in the line, phase B will also lag by 120 degree to phase A. So therefore the current in the line B will be 5 minus 66.87, because 53.13 minus 120, it will be 53.13 minus 120, it will be minus 66.87. Similarly here I can find just by adding it 53.13 plus 120 degree. So it will be 173.13, right? Now I found the line currents, so I can easily find the phase currents here, right? So the phase currents are nothing but it is, we know that line current is root 3 times the phase current and minus 30 degree lagging, right? So therefore I can just find the phase current as this. So your phase current IAB will be line current. This is your line current by root 3 by minus 30 degree, right? So that will give me 2.887, 83.13 degree. That is the phase current. So our purpose is fulfilled. We found the line current and phase current, right? So all other phase currents you can find in the similar fashion with respect to the other line currents. Okay. So now the question is to find VAB, that is the line voltage across this. So VAB will be nothing but IAB into ZAB. Just multiply it, we'll find VAB, right? The voltage across this. That is coming around at the load side. That is the load side voltage, right? So the source side voltage we have around 866 volt, the line to line voltage. But when we are finding the source side line to line voltage or phase voltage, that is, this is also equal to the phase voltage, right? And this is also equal to the line voltage. So it will give me 874.93, 28.87 degree. Okay. Now similarly I can find VBC and VCA just by multiplying the current and the impedance, phase current and the impedance. So now we found the voltage, current, everything. Now I need to find the power absorbed in the load. So power absorbed in the load, how I'll find? I'll find just by multiplying the current, the phase current square, magnitude of the phase current square into 177. That is the resistive element, because in capacitive element there will be no power loss. Okay. So only resistive element is responsible for power loss or power absorbed. So therefore IAB square into 177, that will give me 1475.25 watt. And net power absorbed by the total load will be 3 into single phase load, that is 3 into power absorbed by a single phase. So that will give me 4425.75 watt. And similarly, if we'll find the power loss in the line, so I can find 3 lines, we have 3 into current passing through the line is 5 square, and the resistive element in the transmission line is 1, so therefore 3 I square R, so it will give me 75 watt. So the power absorbed in the line is 75 watt, power absorbed by the load is 4425.75 watt. So now the power drawn from the source will be the power absorbed by the load plus power absorbed in the line. So that is nothing but summation of these two quantities. That will give me 4500.75 watt. I hope everybody understood this problem. So very clearly it is demonstrated. So thank you very much, and we'll continue. In fact, in the next class, we'll not talk about this electric circuit theory. We'll go to the magnetic field. We'll discuss the laws of electromagnetism. Okay. So thank you very much. If you have any question, any doubt, you can ask me. You can unmute yourself, you can ask, or you can write your question in the chat window if you have any doubt.